But now this material, you're actually going to have numbers. This stuff's hard to grade, you know, when you, and it's like, oh, I don't know. But these will actually be numbers. I can see if you got the right number at the end.
Yeah, like math.
Yeah. But volatility, there's no, it's just like a general thing. If a liquid's volatile, basically it evaporates quickly. Why would something evaporate quickly? Well, because its intermolecular bonds aren't very strong. Okay, so volatility has to do with intermolecular bonds. Okay, and there's ways to measure volatility, but.
So I have a question. So my boyfriend's dad, we were talking about volatility. We were talking about evaporation of water. And is it always evaporating, or is there like states where it's not at all? Like.
I think like if you have a glass of water out, it's what's happening is near the surface of the water, those water molecules are getting enough kinetic energy to break their intermolecular bonds, kind of like that video we saw. And so, yeah, it's evaporating. But like in weather and stuff, we learned that, and you guys already know this, that if the air is already pretty saturated, if the air is high humidity, okay, if it's high humidity, then your rate of evaporation is less.
Yeah.
So the rate of evaporation is different, but.
Yeah, because I got interested so much on the internet. Yeah, I just wanted to hear you.
Yeah.
Yeah, that's pretty much what they said. The rate is different, but
Yeah.
it really never stops evaporating.
Yeah. I'd say that's right. So I actually drew these funky looking things, and I'll take little snapshots. And I did. I know it's ugly, but you should see what I have to draw. It's like this little tablet thing. So
Like that one? I'm just kidding.
no, it's different. Maybe if I held it like that, it'd be better. But I don't know. But from left to right, we have two liquids, and it's my proverbial like beaker with a little pressure gauge along the side of the beaker. So it's sealed, and it's like what we were talking about, the water evaporating. You give it enough time, and it will establish, basically it will saturate this headspace right here. Okay, that's kind of what it's saturated. And depending upon the volatility of the liquid, now this is both at the same temperature. At the same temperature, the more volatile substance will have a higher equilibrium vapor pressure. And so I'm trying to kind of show this gauge kind of going higher equilibrium vapor pressure, more volatile, and that's why I tried to show more dots there. Okay? If it's less volatile, if this is a different liquid, it is a different liquid, it's less volatile at the same temperature, it's going to have a lower equilibrium vapor pressure. Okay? It's dependent upon the stuff. And we could kind of look at two substances again, one volatile and one not as volatile. But in this case, what if we want to jack up their temperatures, monkey with their temperatures so that we had the same equilibrium vapor pressure? So when I drew this, I don't know if you can tell, but in the head spaces above these two liquids, I have the same number of dots. So that's my vapor. Okay, so they're at the same equilibrium vapor pressure. But if this is more volatile, you have to lower the temperature to get them to be the same equilibrium vapor pressure. Okay? Because it's more volatile, so you have to tone it down. You have to chill it down. Okay? And it is a little bit about kind of like a statistics and a bell curve kind of which liquid particles are going to have enough kinetic energy to break their intermolecular bonds and become a gas. Okay, so that's kind of just general volatility. What is volatility? So now I have a curve coming up, and you can probably already see it to the left here. But on that curve are 5 different substances, substances A through E. And I thought we'd go ahead and take a look at them right quick and think about what their volatility would be like. So diethyl ether is the first one. It'll be in red, it's A. And diethyl ether looks like this. And I've been kind of harping that if you see these kind of hydrocarbon ends, they're nonpolar. The ends are nonpolar. Okay, that oxygen right there would actually bring a bit of polarity, and it would be partially negative. It does look pretty darn symmetrical, too. These are actually listed in order of increasing bond strength. The next one is benzene, and benzene is right down here. Benzene is just benzene. It's that C6H6. Okay, it's the benzene ring, alternating single double, single double. Then next on the list for increasing polarity would be H2O. It's relatively small, but by golly, it can hydrogen bond. Followed by following water actually is toluene. Now toluene is a benzene ring where one of the hydrogens has been substituted as CH3 group. We call this CH3 group a methyl group. So right there, it's methyl group. Now you might say, but Mrs. Snipes, you know, if the benzene ring is nonpolar and the methyl group is nonpolar, then you have basically put something that is generally nonpolar in with more bond strength than your my water. And I would say, well, at that point, your dispersion forces are kind of kicking in. But here in a minute, you're going to see those curves are kind of close together. The next one, the last one, actually is a benzene ring where a hydrogen has been substituted out. An amine group, NH2 is amine, so an amine is there instead of a hydrogen. Now the cool thing about amine, remember, is that actually fits the criteria for hydrogen bonding. NH2, anytime you see that, think hydrogen bonding. Because we said if you have a hydrogen connected to an oxygen, or a hydrogen connected to a nitrogen, or a hydrogen connected to a fluorine. Okay, so here's our curve now. This is actually called an equilibrium vapor pressure curve. Equilibrium vapor pressure curve. So notice along the x-axis what we have are temperatures. Of course, you see the different colors for the different substances. And at a given temperature, we see the equilibrium vapor pressure for that substance. So I already said diethyl ether is the least or the most volatile. Here's diethyl ether. So notice if we pick 20 degrees Celsius, okay, look what its equilibrium vapor pressure is going to be. 400 millimeters of mercury. If we pick 20 degrees Celsius, the blue one is benzene. Look what its equilibrium vapor pressure is going to be. Oh, maybe 55, 60 millimeters of mercury. That's the blue line. The green and the black line actually are toluene and water. So there is kind of a little bit of a, kind of one is more volatile early on, and then the other they kind of switch here. But about 20 degrees Celsius, you're looking at a relatively low equilibrium vapor pressure. Okay. Now at 20 degrees Celsius, actually aniline, as it turns out, is it has a very low equilibrium vapor pressure. Aniline, hydrogen bonds, large dispersion forces working. So remember, though, on this equilibrium vapor pressure curve, actually is, this is the, how do we say this? You can find the normal boiling point temperatures. If you look at what temperature will their equilibrium vapor pressures be, 760 millimeters of mercury. At what temperature will they boil? So let's pick on water. Water is black. Okay, so here we go. Where does water intersect temperature-wise? Okay, at 100 degrees Celsius. Water boils at 100 degrees Celsius. Equilibrium vapor pressure for water at 100 degrees Celsius is 760 millimeters of mercury. Okay. What's the normal boiling point temperature of the blue one, benzene? What do you think? Maybe 80 degrees Celsius. The normal boiling point temperature of the red one, diethyl ether, maybe 37. Okay, so that's how you do that. Okay, so those are equilibrium vapor pressure curves. So I went ahead and highlighted this spot right here because the next problem we're going to work deals with water. So it's the black curve. and it's at 25 degrees Celsius. So I know you can't really pick this off, okay? But this might be easier. This is for water. This is basically tabulated data of the curve you just saw, part of the curve you just saw. Because along the x-axis, we had temperature. Along the y-axis, we had equilibrium vapor pressures. This is for the substance water. So here in a minute when we work this problem, it happens to be at 25 degrees Celsius. So the equilibrium vapor pressure for water at that temperature is 23.76 millimeters of mercury. All right, so let's work a problem. See, I drew that picture too. Okay, so it's not a beaker, but it's in an Erlenmeyer flask with a sidearm where we have a pressure gauge. I've never seen one of these, but this is just what I pictured. So the problem goes something like this. Basically, you have a puddle of water at the bottom of your Erlenmeyer flask. The mass of the puddle of water is known to be 0.110 grams. The volume of the flask, it's stoppered, so it's closed. So the volume that can be contained is 5.35 liters. The temperature is 25 degrees Celsius. So that's setting up the problem. The question goes like this. It's a classic. So basically, they say verify that given this scenario, that entire amount of water, 0.110 grams, verify that all that liquid will evaporate. Verify it will evaporate, and say what the partial pressure of water is. Okay. Well, they kind of give you a hint, verify that it will evaporate. So it's like, well, you know it's not going to reach saturation. It's actually all going to go from a liquid to a gas. So you figure it's going to be under the equilibrium vapor pressure for water at that temperature. That's kind of a hint. We're going to assume that it follows, and you guys are going to have to use or get to use. A lot of times students like this. The gas laws, PV is equal to nRT. You're going to assume ideal behavior so that you can use PV equals nRT. So we're going to work two problems that, kind of with similar situations. And in both cases, you have two ways to work it. Okay, so the two approaches kind of go like this. Okay, we could go ahead and we could calculate what the pressure would be if that entire amount, 0.110 grams of water, if it entirely evaporated, given the volume of the container and the temperature it is. Okay, assuming it all evaporates. So if we assume it all evaporates, okay, then we come up with a pressure. We can compare this pressure with the equilibrium vapor pressure from the table at that temperature. Okay, and if our calculated pressure, if it all evaporates, is under the equilibrium vapor pressure, then basically you haven't maxed out. It will all evaporate. You have room for more to evaporate. If you come up with a pressure that's higher than your equilibrium vapor pressure, that can be contained with that volume at that temperature, then you're going to have residue left over because it really can't all evaporate. It won't all evaporate. Your pressure that you calculated cannot exceed the equilibrium vapor pressure at that temperature. So alternatively, we could go ahead and forget the water, that's the puddle of water for now, and just basically considering the volume and the temperature, come up with the maximum amount of water that could fit. Okay. And then once we do that, we can just basically compare that mass to the puddle. Okay. So if the mass that can fit is more than the puddle, okay, then all the puddle's going to go away. Okay. If the mass that can fit is less than the puddle, then you're going to have residual left. Okay. So those are the two options. And so in this case, since a couple of things, they kind of alluded to the fact that it will all evaporate, and plus they wanted the partial pressure of water vapor in the first place. If you do the first approach, you're going to go ahead and get that anyway, right away. So we're going to do the first approach for this. So the first approach basically says we're going to let that entire mass of water evaporate. Okay. So in this, and we're going to solve for what the pressure is. So basically, N is going to be from our 0.110 grams of H2O. Of course, we need to use the molar mass of water to get from grams to moles. That's what the N is. R is the ideal gas law constant. Temperature was given. We got to convert it to Kelvin. And the volume was given. So back in Chem 1, when we talked about converting something like grams of water to moles, we would take you'd have to show, it's not funny, but you still have to go ahead and show this, coming up with the molar mass of water, but you probably already have it committed to memory. So to convert it, then we take the 0.110 grams of H2O times 1 mole of H2O over 18.02 grams of H2O, so our grams cancel. So that's our N. So the moles that we're going to use are 0.00610 moles. And what else we got? Here's our little box of goodies. So the N is 0.00610. The temperature was given 25 degrees Celsius. We need to convert that to Kelvin by adding 273. So we're back to 298 Kelvin. And of course the volume is in liters, so that's ready to go. 5.35 liters. So when you work these, don't forget to include your units when you work them. So the partial pressure of the water vapor, if all of that liquid evaporates, would be equal to, in the numerator, 0.00610 moles times the ideal gas law constant, 0.082058 units of R, our liters, atmospheres per mole Kelvin, times the temperature, which is 298 Kelvin, all of that divided by the volume, which is 5.35 liters. And remember, good practices, solid practices of rounding. Looks like 3 significant figures. So rounding to 3 significant figures, the partial pressure of the water vapor is 0.0279 atmospheres. So remember, in this approach, we're going to compare that pressure with the equilibrium vapor pressure at 25 degrees Celsius. The problem is that the table gives it in pressure, equilibrium vapor pressures, as millimeters of mercury. So we basically got to backtrack this from atmospheres to millimeters of mercury. Either that or convert the equilibrium vapor pressure from millimeters of mercury to atmospheres. But if we convert this to millimeters of mercury so we compare it, 0.0279 atmospheres times the exact relationship, 760 millimeters mercury over 1 atmosphere. So units of atmospheres cancel. So it's kind of looking like as you work problems, you're going to want to remember that exact relationship. So atmospheres cancel, and now we know the partial pressure of water is 21.2 millimeters of mercury. So from that table, we picked off 25 degrees Celsius from the table has an equilibrium vapor pressure of 23.8 millimeters of mercury. So finally, you can compare them, and you can say, if all of that water evaporates, you're at 21.2 millimeters of mercury, which is under what we call saturation. It's under the amount that it would hold at equilibrium. And actually, you're done then. You've done both. You have verified that it all will evaporate, and you have come up with the partial pressure of water, which is right there. You pat yourselves on the back. Okay. If we had done the other approach, we would have come up with a mass that's greater than 0.110 grams of water that could occupy that volume at that temperature. And then we would have still had to do this work. Okay. So, let's do another one. And I have another picture. Oh, I don't have a little pressure gauge on the side there. You'll have to just imagine it. Again, it deals with water, and the mass of the water is 1.25 grams. We have a higher temperature. Instead of 25, it's 40 degrees Celsius with two significant figures. The volume of the flask is 9.70 liters. Okay, so here's the question down here. Verify that given the situation, not all of the water will evaporate. So you're going to have a residue, basically, is what they're saying. It's hint, hint. Verify that it will not all evaporate. Come up with the partial pressure of water vapor, which I was thinking about this. I'm like, it should be the equilibrium vapor pressure because it's, okay. Determine the partial pressure of water vapor. I think you can pick that off of the table. But the next bit you can't pick up off the table. You have to say how much of the 1.25 grams will not evaporate. How much you can have left. Okay. So I have a few things to kind of, so it's 40 degrees Celsius, right? You're like, oh my gosh, 40 degrees Celsius, what a pain. Okay, you could like extrapolate or something. Okay, we could try to get it off of this one. This one right here. Remember, the black one was water, so we could kind of go up here, okay, and then go over, right, for water. And as it turns out, actually, my builds didn't work. As it turns out, it is 55.3 millimeters of mercury is the equilibrium vapor pressure of water at 40 degrees Celsius. Or, and you guys are going to be using this for your homework, I'll just put HW. You guys don't have this, do you? This last one. Or you could have this handy table that's in your textbook and simply find 40 degrees Celsius and pick it off right there. That's even better. Okay. So that's what we'll use. So again, kind of the two strategies. We could assume that it's all, we could assume that it's all going to evaporate, which we do know it's going to evaporate. It's going to give you a residue. But in this case, remember, we come up with a partial pressure, and we compare it to the equilibrium vapor pressure at that temperature. And what we're going to do, quite frankly, is you would come up with a higher equilibrium vapor pressure than is allowed. And that's not going to get you down the road. This other approach will get you down the road to coming up with the mass of water that'll be left, what's your residue. Because remember, in this other one, what we're going to do is we are going to consider the volume, which is 9.70 liters. We're going to consider the given temperature, converted to Kelvin, that is 313. And we're going to consider the equilibrium vapor pressure at 55.8 or whatever it was, millimeters of mercury. Okay. And then given those four parameters, those three parameters, ideal gas law constant, we are going to go ahead and come up with how much water will maximum be in there in terms of moles, and then convert that to grams. That will get us down the road because we know that there's more than enough water to go ahead and to what we say saturate. You're going to have water left over. So the second approach is the best. So here we go. In this case, like I said, we're going to go with P is going to be our equilibrium vapor pressure at that temperature. Volume was given, of course R we know, and the temperature we can convert from Celsius to Kelvin. So if you need that table for your homework or anything, that equilibrium vapor pressure table, not curve, but table, it's on page 513. And so from that, we picked off for 40 degrees Celsius, 55.3 millimeters of mercury. Remember, if we use the ideal gas law constant we've been using, we have to use pressure in terms of atmospheres, not millimeters of mercury. So we have to convert are 55.3 millimeters of mercury. If we multiply it by 1 atmosphere per 760 millimeters of mercury cancel, and we're left with atmospheres. So don't forget that kind of important conversion before we work this problem. If when you work the problems, ideal gas law problems, if you're careful and including the units of R, this will hit you in the face, because your atmospheres won't cancel, and you're left with millimeters of mercury and atmospheres. Okay, so let's substitute in the mole. Okay, so we have the pressure, 0.0728 atmospheres. The temperature was 40 degrees Celsius. We need to add 273 units. Remember, there's a decimal after the 0 for 40, so that means the uncertainty started at the ones place, so we're allowed to the nearest ones. 313 Kelvin. The volume was given 9.70 liters. Now we're ready to plug in. Now remember, I said when we worked these in Chem 1, one of the hardest things with using PV equals nRT is making sure you get your algebra right. I don't know how many times I've seen it like flipped, and I've probably done it before, too, but just take your time rearranging. Okay, so let's plug in. So the number of moles of water molecules that would fit at saturation would be 0.0728 atmospheres in the numerator times 9.70 liters, also in the numerator, divided by, in the denominator, you have the ideal gas law constant, 0.082058. Units of R are liters, atmospheres per mole Kelvin, and then times the temperature in the denominator, 313 Kelvin. So we haven't done cancellations recently. Let's see. It looks like atmospheres here cancel with atmospheres here. Liters cancel with liters. Down here, then, that leaves us with kelvins will cancel with kelvins. Here now we have basically 1 over moles. And that's equal to moles. So our units are great. Looks like we round according to 3 significant figures, and you get 0.0275 moles of H2O. And you're close. You're very close. So in order to see, we need to see what mass that is. So we take those moles, 0.0275 moles of H2O. Now we use the molar mass of H2O, 18.02 grams of H2O per 1 mole of H2O. Round it to 3 significant figures. That means the mass of H2O that will evaporate is 0.495 grams of H2O. So the amount that's left is just a subtraction thing. So we were given 1.25 grams. Now remember, since we're subtracting, we are conservative with regard to decimals. So we round according to decimals. So here we have 2 decimals. Here we have 3 decimals. So we're only allowed 2 decimals actually in our answer. So regardless of whatever your calculator gives you, you have to round it to 2 decimals. And that's the answer. Can't remember on my builds, do I answer so what's the equilibrium vapor pressure? But to me, the equilibrium vapor pressure, are you guys good with this? I mean, I shouldn't say the equilibrium vapor pressure. I should just say, what will the partial pressure of the water be? It will be 0.0728 atmospheres, or the millimeters mercury if you want it to like this. Okay? So then my last little remark or thought here, okay, is sometimes these will say that it's done in a vacuum, which would be the absence of other gas particles. But honestly, even if there is air in your flask where your evaporation is occurring, how do I say this? The air is nitrogen and like 80-20, nitrogen, oxygen, 20%. So the nitrogen and the oxygen in your flask, put it this way, the water vapor behaves independent of those other particles that are in there, those other gas particles that are in there. Okay? Okay, so, man, that went fast. I didn't talk too fast. Oh well. Because this is all I want to do. We're going to take a look at these. And then we'll call it a day. While I'm thinking of it, the next is the Clausius-Clapeyron stuff, right?
Mm-hmm.
Okay, so we're going to hold that back because that's not next week's lab. I think that's the next week's lab. So Monday's lecture will pick up, I believe, on part 4, solubility. Okay. So let's take a quick look at these, and then we'll come back to the CC Clausius-Clapeyron plot stuff. All right. These are, I think I might have mentioned before, these are like, I did these last year, so let's see what we think. And so they're kind of backwards. So here's 29. Okay, so 29 looks like this, where you have the element bromine. You're taking liquid bromine and closing a container, okay, and you're allowing it to basically saturate the air above it. Then the question goes like this. You're supposed to come up with the partial pressure, what's the pressure of Br2 gas? And notice that they go ahead and they give you a volume of that gas, 250 milliliters of that gas will contain, and it gives you a mass, 0.486 grams of gaseous bromine, Br2. So from that 0.486 grams, you can go ahead and get the moles of Br2. So you can get the moles of Br2 gas, you have the volume, you have the temperature, you can knock out pressure. That's how that one goes. And then, so if you're looking at my, my hints or whatever, the 29 is the end. So it goes 30, blah, 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 and then 29 is at the end. So this is 30. 30, again, has basically you have a pool of acetone down here. Acetone's a relatively volatile substance. It will fill the flask. And it tells you that once the liquid is in equilibrium with the gas, that the density of that gas is 0.876 grams per liter. So we've done this before. If they give you a density like that, you can do a 1 liter basis, and by golly, if you do a 1 liter as your volume, you know your volume and you know your mass, because it's 0.86 grams per liter. So that's what we're going to take as our basis. Notice the temperature is given. We need to convert it to Kelvin, and we're supposed to find the pressure. So that one's not too bad. Easy for me to say. These, I have some kind of, I think they're almost kind of cheesy. Pressure cookers actually are kind of neat because notice that as you jack up the pressure, the boiling point temperature increases. So pressure cookers, remember we said like if you climb a mountain that actually water will boil at a lower temperature? Did we say that the other day? Okay, good. It boils at a lower temperature. Well, just the opposite. That's low pressure. If you take something and you pressurize it, it'll boil at a higher temperature. So pressure cookers make use of that. And this table kind of does that. So it says, if you have a pressure cooker and it's set at 2 atmospheres, what is the, at that pressure, what temperature does it boil? So we can use this, okay, but we have to convert atmospheres to millimeters of mercury because that's how this table reads. So convert atmospheres to millimeters of mercury and find it on here, and then that corresponding temperature is the temperature it will boil at. Again, the same table. For A, it says the boiling point, it says what is the boiling point if the pressure is 640 millimeters of mercury. And so, actually, my hint here is, the problem is you don't have 640 millimeters of mercury here. You have 633 or 634 and 658. So just do your best to estimate, okay? Long time ago, anyway, so do your best to estimate.
So there's no like set answer then for that
Right.
part, it's just kind of.
Yeah.
Okay.
Yeah. The next one is kind of silly, I think. So let's say it boils at 94 degrees Celsius. Okay, that must mean that you're climbed a mountain, temperature's boiling a lower temperature. What is the pressure there? And this one, all you got to do is pick off 94 degrees and write down the corresponding pressure. Yep. Okay. Then the next two kind of go together. The next two are similar in that they have an inner carrier gas that's bubbling through something that's volatile. Remember we looked at aniline a little bit ago? Wasn't aniline the benzene ring with the amine group, the NH2? Okay. So in this case, we have a certain volume. Helium is our inert gas that's basically going to bubble through aniline. Your problem says that the helium's going to dwell long enough to go ahead and become saturated and be collected over there. The temperature of the helium gas is given. The temperature of the aniline is the same as the gas. They tell you how much you had in your liquid aniline tank before and how much you had after. By difference, of course, you can get the mass of the aniline that got incorporated into your carrier gas. Once you have the mass of the aniline, basically, of course, you can, from mass of aniline, you can get to moles of aniline. The molar mass of, the formula for aniline is given up there, C6H5NH2. So you can get to the moles of aniline. Once you have the moles, of course, you have temperature, you have the volume that your helium aniline mixture was confined to at the end, so you can knock out the partial pressure of aniline. But my least favorite one, I shouldn't tell you that, is this one. So the carrier gas now is not helium, it's nitrogen, and we're going to bubble it through carbon tetrachloride. Nasty stuff. The volume of your carrier gas and the pressure of your nitrogen and the temperature we're given. The temperature has in common of the analyte that you're going to pick up. And it's going to be collected. So over there on the right, you're actually going to have a mixture again, nitrogen and carbon tetrachloride. But this is a little bit different because they give you This is a little bit different because they give you the total pressure of this thing over here. Like you figure this thing over here has your nitrogen and your carbon tetrachloride. And those pressures are additive. Okay, so the combined pressure is 742 millimeters of mercury. Luckily in the problem they say at this temperature, which is 45 degrees Celsius, they say that you figure the partial pressure of carbon tetrachloride is going to be 261 millimeters of mercury. So by subtraction, you can massage that total pressure and get to the pressure of nitrogen by difference. So that's not too bad. Bottom line is they're after V over there on the right. They're after the volume of that container. I was going to look back at my notes. I'm like, really, Livy, is this how you did it in your answer key? Because it seems so convoluted. So we can get to the partial pressure of nitrogen that way. And to get to the volume of the container, I went through nitrogen. I'm not sure if you have to, but I did. So if we're focusing on the nitrogen to get to the volume of that container, we can actually revisit this one over here and get to the moles of nitrogen that must have been passed through based upon the volume, pressure, and the temperature of the nitrogen gas. So now we have the moles of nitrogen. We have the partial pressure of nitrogen from that. We have, of course, the temperature, and the volume is what you're solving for. Like I said, on my list of things to do this afternoon, which I didn't, was to say, is this really the best way to work it? No. we might find a better way to work it, I guess is what I'm saying. Okay? So I think that's kind of it. Because then with regard to nitrogen, you're gonna know the partial pressure, the moles, and the temperature. It's all for the volume. The shared volume, but, okay? All right, cool, that's all we have. So we'll start on part 4 on Monday.